Hi everyone, welcome. My name is Garrett Eardley. I'm a software engineer at Riot Games. For the past 2.5 years, I've been working on our distributed backend systems, scaling those systems out, adding new features. So things like matchmaking, where we take a pool of players in League of Legends and we sort of munge them all together and find optimal matches for all of those players. Or processing games as they finish, so processing stats, auditing that data, and sending that back out to players so that they can view it. And for the past 1.5 years, I've been able to focus on building a new stats platform to power League of Legends and Riot Games. So that's what I'm here to talk to you today about. We have a number of challenges that we face with our existing legacy system that we wanted to solve as we're building this new platform. And so we made some technology choices, and those choices made us think about how we manipulate our data set and do modifications a little bit differently than we did in the old model. So in order to do that properly, I'm going to give you some context on Riot Games and League of Legends, jump into our legacy system, sort of show how that's evolved over the last couple of years into what it is today, show you the high level of the new system, and then get into some of the data patterns that we're now following in that system to build new features. And then wrap it up with a couple things about where this system's at and what we're doing with it today. So let's jump into the context. So Riot Games, our mission, we aspire to be the most player-focused game company in the world. What that means is we are striving to improve our player experience every day. That is our main focus as employees at Riot. So from like an operations sense, doing everything to minimize downtime so our players can continue to play the game. Build in more fault tolerance into the system, or as a designer, tweaking gameplay so that the game is more balanced, fun, and fair for our players. So League of Legends, for those of you who don't know what it is, we launched the game back in 2009. It's a team-oriented game, so you team up with 4 other players on your team and against 5 opponents. You pick from one of 100+ champions and sort of battle it out to see who wins. So from a player standpoint, what you do is you log into our client, you go ahead and matchmake into one of our different queues, and we have several different game types that you can pick from. And I'm just going to go into our classic game type on our Summoner's Rift map real quick. So you matchmake, we match you with other people of your same skill level, and here you need to pick a champion. So you're coordinating with your team, chatting with them, figuring out which roles you're going to fulfill, they're going to fulfill, and sort of synergize. So a lot of thought is going in here. Meanwhile, the other team is doing the same thing. So you get in the game, and you go ahead, run around and kill stuff, and that earns you in-game gold. You can use that gold to then go ahead and purchase items. These items power up your champion, let you do more damage, whatnot. Eventually, you're going to kill some dudes. And then in order to win a match, you have to push into the enemy team's base and blow up their nexus, which is the sort of central command structure of each team's base. So you win, victory, hooray. And then we present you with an end-of-game scoreboard, and this is showing the stats from that game. And so this is what players can use to sort of self-develop themselves. They can analyze, oh, I did bad in this aspect, or I did good in this aspect, I need to work on this the next game. And so there's a number of metrics that they can use here, but it's just an end-of-game snapshot of all of these metrics. And there's a lot more detail that we think is valuable for players, and it's also valuable for us to help inform some of the decisions we make. And so we needed a system that we can suck in all this data and do something with it. So our legacy system wasn't up for that task. We are supporting somewhere around above 5 million concurrent users today, and we had never in our lives imagined that we'd grow to be this big. So our initial target when we built this system was 20,000 concurrent users in a single environment. And we were going to be very happy if we reached that point. So we were a startup, and so we gave ourselves we didn't give ourselves, we had a short dev window in order to build this platform to support League of Legends, get it out the door so we could launch the game. So we made some compromises along the way as we were trying to build this minimal viable product. So all the core functionality that we needed in order to launch, nothing more. But we consciously incurred tech debt. We made the choices that would let us get the product out the door faster, even though we knew we were going to have some pain further down the road. So let's look at that system and what it looked like at a high level. So we have an app tier where we put all our business logic, a caching layer that gives us some atomic operations on our data set, and that caching layer talked to a single database at that time. You all know where this is going with that single database, but we had a low concurrency target. We only had to support a single environment, and well, that database was going to be our single point of failure. Any problems that we incurred there would take the system down, bring the game down so players couldn't play our game, which is sort of a counter to what we're trying to do on operations and engineering side. And then, of course, as we upgraded our software, upgraded MySQL, or did schema changes to our database, we had to take the entire system down, which means no one could play League of Legends. Not so great. So let's fast forward to 2.5 years, or to the beginning of 2012. We've gone ahead and sharded our database so that we can get some horizontal scaling out of it, a little bit more throughput. But now we've just created multiple single points of failure in our system. If one of these goes down, we're still kind of stuck in the water. We're starting to get really good at mitigating these problems. We can hot swap in secondary slaves that are real quick, but it's still a downtime that we incur and sort of a pain point for our players. As far as how we're structuring our data, we're now using the database as sort of a key value store. Schema changes take a long time on large data sets and the version of MySQL we were using. And so we were storing all our values as blobs in our database so that we could have some flexibility in what we were storing and add new fields in without having to do those schema changes. We've scaled out our cache to keep more of our data set hot and in memory so that we can to keep the load off the database. And now we're supporting 12 of these environments throughout the world. And none of these environments were the same. So we have these 12 non-homogeneous environments. It's difficult to do capacity planning when you have different targets of what we need to support in these different regions. And then tuning became very complex for us. So fast forward to today, we've gone as vertical as we can in our databases. Rather than continuing to go horizontal and try and figure out partitioning, the easiest thing for us was to go ahead and keep going more vertical, SSDs, Fusion IO, et cetera. Our cache layer, we've gone way wider, so we're keeping more of our data set hot in memory. And now we're supporting 30+ regions around the world, still non-homogeneous, so we still have all that pain. And while we've mitigated some of our problems, we really haven't solved our key pain points. One of these databases goes down, and we don't get a slave in fast enough, we ended up taking a large segment of downtime, and our players can't play the game. And the other problem that we have is adding new features into these systems is getting very complex. And when we want to add data-heavy features there, it's something that we opt out not to do because we really can't under this model. And so we needed to build a new system. So some of the challenges that we wanted to solve with that system, get rid of single points of failure. So that any box can go down and we're still up and running and servicing our players. Get rid of downtime when we do hardware or software upgrades. So if we need to bump up to a bigger box on one of our nodes or replace a failed DIMM stick, we can take that node down and not have an outage. And then we want every component needs to be horizontally scalable seamlessly. So that persistence layer was our problem in the legacy system. So we needed a persistence layer that would let us keep going out and out and out. And then, of course, whatever we chose needs to be able to support these new data-heavy sorts of features that we want to give our players. and that we need in order to do analysis on our gameplay and make good decisions for our players. All right, so let's get into the meat of this. The new system, it's actually pretty simple. We got rid of the cache layer. We still have an app tier with all our business logic in it, and we're using Riak as our data store. Riak has a couple nice properties to it that solve a lot of those challenges. So each node in Riak is, it's not a special snowflake. If one of them goes down, some of the other nodes will pick up the slack and sort of handle that node's request for a while until that node can be brought online. And so we don't have any single points of failure with that. We can go ahead and do rolling upgrades. Basho has I guess, steward of Riak. They've committed to make sure each new version of Riak is compatible with the older versions of Riak. So as we're going to new versions and we want some new features, we can roll that out to a single node, make sure that that node is doing fine, and then start going out to the rest of our nodes in the cluster seamlessly. And then Riak has hot rebalancing. So if we want to add nodes or remove nodes from the cluster as we're scaling up or scaling down, Riak will go ahead and move its data around to those new nodes so that the load is evenly distributed across the system without causing too much impact to the system while that's occurring. All this together lets us do some of those data-heavy features. We can just keep adding nodes in there as we want to have more data accessible hot. Some of the other nice things about Riak is the multi-data center replication, their enterprise edition. So we can have one cluster in one data center on one part of the country, another cluster on the other side of the country, and replicate between those two in sort of a master-master type of situation, so that the data set in both is up to date. And if we experience some sort of network outage in a data center or that cluster goes completely down, we can fail over to the other node, and we have most of that data available for servicing queries. Riak works a little bit differently than our caching layer did and MySQL. It's a NoSQL solution, key value for the most part. And so I wanted to run through the normal get and put cases so you guys have a better understanding of the challenges this eventually consistent system posed for us as far as updating our data. So a get or a put comes into one of the nodes. Any nodes can handle any request. And it'll go ahead and forward that request onto the nodes that have the piece of data for the key that you're looking for. So it'll issue that get to node A, B, and C. And it's just waiting for some number of those nodes to respond, not all of them. It's tunable eventual consistency. So we could say, oh, we only need 2 records to be written before we return a response to our app layer, or we only need to read one of those records to return a response to our app layer in order for that operation to be successful. And then when that final node responds, hey, I wrote it, nobody really cares. It's great that it was written, so we have that other replica, but there's no one hanging on the other end waiting for that response. All right, so when a node fails, you run into a case where, so node C here went down. Node E will go ahead and hand that request off to the other node in the cluster here. And in the case of a put, it will actually store that value. And so when node C comes back online, it'll go ahead and hand off that data to node C. So node C is up to date with all of its data. As you can imagine, now that we're not waiting for the data to be written in all of our replicas, we could get multiple versions for any given key in our data set. And so we had to deal with, had to start figuring out how we're going to deal with conflict resolution. If I read a key and I get 2 distinct values back, which one do I choose? Do I take parts from one and parts from the other? And so we had to put a good bit of thought into what we're doing there. Idempotent operations. So if we're processing the same game over and over again, we don't want to be corrupting our counters and adding this value over and over again. So sort of designing our data structures to account for those problems. And then on the data heavy side, balancing the number of gets that we do for a particular query against our application versus how big the objects are that we're storing inside of Riak. So a good example would be our, say we have several different types of counters, one for each of our 100 champions for each player. And if we stored each of those values, each of those aggregates for each champion into a separate key, but we wanted to serve back maybe a particular type of a class of champions aggregate data, we'd have to issue multiple gets against the data store in order to service that request. Whereas if we put all these aggregates into a single object, now that object size is a couple hundred K, and we have to read and write those every time we want to modify just a small segment of it. So there's sort of a balancing act that we had to approach there. All right, so we've come up with a couple different data patterns in order to deal with those sorts of situations. So I'm going to start off with the easy parts and then move on to the harder bits. So let's start with the raw data, really any sort of statement of truth in our system. When I play a particular game and I get some stats at the end of that game, those stats don't change. So if we're processing that same game over and over again, it's still going to say I got 5 kills or 10 deaths. And so it doesn't change. So here's a JSON representation of a game. Got 2 kills, 3 deaths. And that data is never changing. So this is sort of the trivial case. And we just let the last write win as we're storing this. So if we do have a conflict, we just choose the one that was written latest. And when that conflict occurs, the 2 siblings actually are the same value. And then as we're taking in data, we just store it. We don't care what we actually had. Well, we do care what we had, but we don't care what we had, and we can just go ahead and write over what was there in this raw data case. So let's move on to something a little bit more harder, something mutable. Let's look at somebody's match history. So in this case, you can imagine it as like a 1 to n index. One player mapping to all of the games that player has played. So here we're showing recent games inside of our client of what games I've played recently. So let's walk through modifying that. So I just finished game 1, 2, 3, 4, and I have these 3 games that we currently have stored in the system over here. And all we do is we just read in that old value, add in that new game ID to the match list, and write that back into Riak. So you may be asking, so what happens when you do concurrent updates and cause multiple versions to exist in the system? How do you handle that? So we have these 2 deltas that are coming in at the same time. Maybe we got backlog somewhere. And we create these 2 siblings for my match history in Riak. And so that they're not the same. One of them has one game ID, another one has another game ID that's not existent in the other sibling. On the next read, we're going to go ahead and resolve that conflict. So we read in these 2 values. We just do a set union in this case. The match list, you can imagine it as a set that is just growing over time. We're not removing data from it. So we can do this sort of simple operation in order to have the match history continuing to update. What if I just want my TMO games? So I didn't have any context about those game IDs in my match history. What if I want to do a more complex query here? Well, what we do is we just add non-primary indexes into the record. So we track what champion a player played, whether they won or lost, queue, a couple other fields that aren't shown, in order to do quick slicing and dicing on a list of games. This adds a little bit of overhead, but since we're only mutating this object, I don't know, every 40 minutes or every 30 minutes at the best case as players are playing games, this data set can't grow too large, even over a longer period of time, especially since we limit what we're filtering criteria that we have here. All right, so what about something a lot more complicated? Aggregate stats. So here we're showing various stats by each of the champions that players played as. And so you can imagine these as sets of counters that are mutating as somebody plays a game. In the simple, trivial view of the world, I had this change coming in where I have 3 more deaths, or 3 more kills, and I've had 100 kills in my career as a League of Legends player. We go ahead and read in that value on the right-hand side and add to the counter. Problem is, what do we do when we get concurrent updates and we're doing something as trivial as that? We get these 2 siblings that you can see on the right-hand side that have distinct values. There's no way to resolve what we have here without adding additional info into what we're storing. So why don't we keep a list of deltas? That's sort of like what match history had. So let's look at that. So now we have this, these deltas come in, and we can just do a set union, right? So it's resolvable when our conflicts occur in the data store. Problem is, it gets really expensive if we're tracking hundreds of metrics for each game that we want to aggregate across. So as players are playing more and more games, these object sizes are growing into the megabyte or even larger range for each of our players. So when a game comes in and we modify this, well, that means we have to write a meg for each game, and this is sort of that balancing act that I was talking about before. So how about we combine this, where we keep a list of deltas, with keeping a sort of truncated aggregate, and that's what we do. And so here we've got on the delta side, we're now tracking a game ID, the timestamp of that game. And then on the what we're storing side, we keep a truncation time. And that truncation time represents the last time we modified this truncated stats field. And so that's all my really old games that I went ahead and merged together. And then for more recent games that I played, I keep a recent games list. So I can sort of, as I get conflicts in that recent games, I can do a set union. So here's how it looks in a little bit more detail. So we went ahead and we've merged 2 siblings that had different recent games lists. And what we do here is we look at the truncation time and we say, oh, we want to truncate anything that's older than a particular max age. And so in this case, we can take game ID 1, 2, 3, 4 and sort of merge it up into the truncated stats value that we're writing over on the right-hand or left-hand side there. And then meanwhile, we're updating that truncation time to represent the last game that we've merged in here. And the recent games list has that, just the most recent games inside of it. This is not a perfect solution. If we had a long network partition where we're updating 2 separate versions of this value for a long period of time, that truncated stats value could get desynced from between each of the versions, and we can't resolve that conflict still. But we would have to have a particularly long outage without doing a resolution in order for that to occur, which should be a rare case. And when it does occur, since we have all this raw data that we're storing now, we have these longer match histories, we can go ahead and query that match history, get a list of games, query each of the pieces of raw data, and rebuild this object. That's an expensive operation, so we're doing everything in our power to make sure that doesn't occur. All right, what if I just want to know how many times Timo dies? And I forgot to mention earlier, Timo's one of our champions. He's a ruthless killer that people love and more so love to hate in our game. So what if I just want to know when he dies or how many times he's dying? So we got hundreds of updates to the same key coming in for each of our app nodes. So this is a high frequency sort of sets of counters, global aggregates. So hundreds of updates coming into the same key every second for each app node. We can't keep a list of deltas. That list is growing really quick here and would be a little bit hard to manage. So what do we do? Well, so in each app, each of our nodes, each of those nodes keep their version of the global aggregate in memory. So app A may be processing one set of games, app node B might be processing another set of games. And it's continually updating this counter in memory. We can synchronize on it, and we can be sure inside of an individual app it's not having, it doesn't double apply or lose data. And then every so often we're writing behind those values back into Riak. So app A can update its version of the Timo death counter. And app B can update its own version. And when we want to serve this data out to the querying system, we can go ahead and merge this together. Still not perfect. If we had a downtime, we lose some of the values here. But since it's so high frequency, we're actually more looking at averages in this case rather than total counts. Being off and being 99% is still adequate. All right, so I'm going to wrap this up, let you guys know where this system's at, some of the things we've done with it. All right, so the system is live but dark. We've been live since January in a number of our regions collecting data in, but we're not worldwide with it yet. And so we can't start switching out that legacy system until we get that worldwide deployment in place and sort of support that traffic. And we want to be very cautious about that transition. We don't want to mess something up and then have one of our regions down for a long period of time because we made this change. And so we're approaching it strategically, get the system up, make sure it's handling the amount of data that we want to put into it, make sure it can handle the query load before we let it affect the player experience. But we have done some things with it to sort of indirectly influence that player experience. So we can do gameplay analysis with this data. So now that we have more detail about every segment of a particular game that is queryable, we can do some detailed analysis and sort of measure what the various design decisions that our live design team makes has on gameplay experience from patch to patch. And so here we're showing when various structures are dying throughout the course of a match. And we've made a recent tweak in I think 2 patches ago. So we were able to measure a before and after picture here and glean some valuable information. The other thing I wanted to talk about is a project that we did for Thunderdome. And I don't have an internet, so I can't show it to you. But I'll talk about it real quick. So Thunderdome is a hackathon that we do at Riot every couple of months. So we self-form teams of 4 or 5 individuals, and we sort of build whatever project that we want to do that we think's fun or interesting or valuable to us as players. And so we took this new system and we combined it with another system that we have rolled out in our public beta environment, our replay system. And we wanted to answer the question, what if I want to watch Timo die over and over and over again? So what we did is we used our new stat system to identify those interesting games, where those events occurred, pull down the replay file for those games, sort of do a video recording, and then broadcast that out onto Twitch TV, which is a video streaming service. So if you want to look at that later, it's Twitch TV/Timo Dies. So that's it. Thank you guys for attending. And if you have any questions, be happy to answer them.